Good afternoon to all the participants, and welcome to the third session of ATAL FDP on artificial intelligence in healthcare. So today in our start session, we are having Sandeep R. And Sandeep, can you hear me?
Yes, sir, I can hear you, sir.
Yes. So Sandeep is currently Associate Professor in the Department of ECE, Vidyavardhaka College of Engineering, Mysuru. And his academic qualifications are, he is MTech in Electronics from Bangalore, BMSc, and PhD from IIT Gauhati. And his research interest includes perceptual image and video hashing, near duplicate images, video retrieval, machine learning, and deep learning. So today, Sandeep will give us insights of machine learning and artificial intelligence and how to use them practically while using various engine platforms of MATLAB. So without any further delay, I would like to request Sandeep to take the session. Thank you.
Thank you, Professor Mehdi. I hope all of you can hear my voice. Is my voice audible? Can you all see my screen? I haven't shared the slides yet. Yeah, can you see the slides? Can you see the next slides? Kindly respond.
Yes, it is coming.
Okay, yeah. So let me turn off the video. Yeah, thank you. Okay. Yeah. So before we start, let me set some of my goals or objectives. Okay. So this would be a hands-on session as told by Professor Mehdi. But straight away jumping into the hands-on wouldn't complete you wouldn't get the whole picture. So what my idea is, we'll have a bit of theory and bit of practical. Anyways, Professor Praveen Kumar Bora has already covered some of the theoretical aspects, and he has given you the practical applications of machine learning or deep learning, artificial intelligence in healthcare. And he cited some of his works, right? But my objective is, how can we do that? I know the time is very limited, and there are a wide variety of audiences from different background, and I want everyone to come at the same level. So with that intention, with minimal knowledge, we will start our session. And I'll be using the MATLAB tool for implementing it. But those of you who have not installed in your systems, or those who do not have the licensed version of the MATLAB, you can also use the online version. And I have already just a minute, it's taking time. Okay, so I already have tried to execute some of the programs that I had using the online version. So that means it is definitely possible for you also to do it. But preferably, I request, it is better to have the licensed version in your system. Fine. I hope it is now, yeah, it is still taking some time. Okay, yeah, not an issue. So we'll start. Okay. Okay, now I have made the full screen, right? So can you see the full screen? Yes?
Yes.
Yeah, fine. Okay. So deep learning with machine learning and neural networks. Okay. So first of all, I would like to have give the acknowledgement. This contents of the slides were taken from the following references: MATLAB deep learning with machine learning, neural networks, and artificial intelligence, Phil Kim, and also practical MATLAB deep learning, a project-based approach by Michael Polzak, Stephanie Thomas. And majority of the images shown in the slides are taken from the public domain, and the creators or authors of the images are highly acknowledged. It's not mine. So with these references and acknowledgement, let me start. This, I like it. I think most of you would have seen it. Humans are hooked. That's why machines are learning. Okay. Anyway, it's lighter, but it has got more meaning to it. And we know that deep learning is a subset of machine learning, and machine learning is a subset of artificial intelligence. But here I would like to stress the key difference between the machine learning versus the deep learning. See, in machine learning, we have the feature extraction separate and the learning as separate. So that means what you require some expertise to extract the features from the input data. So, and then those features will be used to obtain the model. And then we get the output, whether it's for classification or for regression. But the beautiful thing about the deep learning is that we have the feature extraction and learning. That means what? We do not require any expertise. The feature extraction process is also automated, and so entire thing is no automation. You have only the black box input with the output. That's one of the major difference between the machine learning and the deep learning. To be very specific with the common example, I can say that, say, for machine learning, so some expertise, some brain is required to extract the feature, and then we have a model based for the classification purpose. It would say a car or not a car. But when it comes to deep learning, I'm just trying to relatively compare it. But when it comes to deep learning, say for the same input, we have automated both the feature extraction and the model for the classification, and it would not only say just car, but it would say the color is red, make is Ford, model is Mustang, and or whether it's not a car. So we can have a better implementation of the applications that we want to do. And this is a traditional machine learning technique wherein feature extraction plus machine learning is there. As the amount of data increases, the machine learning traditional feature extraction plus machine learning performance is almost saturated. Now it's the era. Deep learning is the buzzword, and it's the era of deep learning. As the amount of data increases, we are expecting the performance to increase more. So you can see that we require a huge amount of data. And finally, I would like to say some points with respect to deep learning and machine learning. Data requirement is huge in deep learning compared to the machine learning. And as told with the examples, it provides high accuracy compared to machine learning. But the thing is, it takes longer time to train, maybe hours, weeks. Okay, that's what it is. Then huge computational load, which would be only be served by the GPUs, so graphical processing units. And then the domain expert may not be required. I have told you, right? But here you require a domain expert for feature extraction, right? Yeah, so we will not go into the definitions and all because which is already covered and various applications, and Sir has already covered classification of machine learning algorithms, supervised, unsupervised, reinforcement, something as new as semi-supervised. So these applications are all already told. What I would like to say is we'll straight away go to, why learning is difficult. I'll only talk about the practical aspects. Say suppose I have this data, a two-dimensional data, some data points are there. Okay, now I think morning someone was asking like which algorithm do I use or which model would fit better. How do I know it, right? Now say for example, it could be a linear model, it could be that is linear regression, logistic regression, or higher order polynomials. Which one? So the thing is which reduces the mean square error. That's one of the cost function. The other one I think could be also the cross entropy. Here I've shown some of the things that has been implemented with mathematical models. So here we have the data points, and this is the model that we have got. This is x-axis and y-axis. So this is a linear. Of course, you can see that intuition itself will tell you that the error is more. But a better fit would be, when compared to linear, would be the logistic one. And this is the mathematical model that's been used to fit this particular data. Okay, and if you want a better accuracy, now we are slowly diving into, you're not happy with this, okay, somehow better. Life is simple, like, yeah, this would do a job better, but we're not happy humans. We want to always improve the performance. Okay, fine, we would go for this. That is also fine. But when you're doing it too much of customization for the given set of training data, we call something called as overfitting. I'll come back to it later, but I've just given you the mathematical implementation for this data points, the model. See, the sixth order polynomial is used to fit these data points. So given the next, we can always fit. Okay. So what are the challenges with machine learning that we have? And here I would like to say that a simple diagram. See, we have the training data, and that training data, of course, when I talk about machine learning, the expertise, the features have been given, that itself will act as a training data, and then a model is generated. Now, to know whether the model is good or not, we check with the data, and we input data and we measure the output. Okay, so but the real problem is that there's always a distinction between the training data and input data. That means what, we have some database, and we would try to build a model or propose an algorithm to it, but when we try to implement that in the real world, the performance may be so drastic. So because what is the problem? The problem is that the input data and the training data is so distinct. Okay, so that needs to be, so that means we want a huge amount of unbiased data, right? As we have told, say, suppose I want to classify these data points, and the simple thing would be a curve, right? That would fit this thing, and then try to separate it. We know that there are certain errors, but that is okay. But what we try to do, we try to with that data, as I told earlier, but we try to do better grouping or better classification. But at the end, if a new data comes, then we don't know whether it belongs to that particular class or the other class. So we're trying to do overfitting, and overfitting has to be avoided using the methods called, let's say, validation or the cross validation. What do we do in validation? Please consider here. Please note that, so suppose I have thousands of videos, or 1 lakh videos I have for the training. Then in that 1 lakh, I may divide. I may keep 80,000 videos for a training purpose, and say 20,000 videos for validation. So this is something called as, say, it's in the ratio of 8:2. So 8:2. So 8:2. Training set is 8, validation set is 2. This is called as validation. The better thing is the cross validation. So instead of keeping this fixed, here it is fixed. Instead of having that fixed, I think we can go for the cross validation, which is random. So here also 8:2 ratio. Again here, this is 2, remaining thing is in the form of 8:2. Again 8:2 ratio. Everything is maintained and is random. And that's how we would get a better model, right? Now, neural network, right? Now, when we talk about neural network, we can say that the deep learning is nothing but the upgradation of the deep neural network. So for that, we should understand what neural network, what is single layer, multi-layer, or deep neural network, and how did it evolve? Why did a deep neural network really become outstanding or performance? But now why deep learning is performing so well? So for that, let's understand what neural network. If you compare this figure with the earlier one, you know that there's an additional block diagram we have, the learning rule. Earlier we had training data given to the machine learning, input and output. Now we have learning rule. So here, depending on the cost function, we would have different types of learning rule. So depending on the cost function, right? Or the loss function, or the objectives. So we'll have different types of learning rule. That's one of the difference between the machine learning and the neural network. I'm sure that you would know this. So here we have the inputs, the weights and the biases, and we have a node which takes the weighted sum of the input along with the bias, and that will be given to an activation function. The output is nothing but is the output of the activation function. So if I have to represent it mathematically, because we want to write the code, then I would say that at this point, it is just calculating the weighted sum of the inputs along with the bias, right? So it will be x1 into w1 plus x2 into w2 plus x3 into w3 plus the bias. Okay, so plus the bias, and that is given to the activation function. Output is finally this is v. I call it as v. So v comes here, and output is phi of v. Okay. So these are the mathematical denotation that we would say. So this is the weighted sum of the inputs along with the bias, and then written in terms of matrix vector notation. V is equal to W transpose X plus B, where W is equal to W1, W2, W3 weights, and X1, X2, X3 are the input vector. Fine. So our final output is nothing but the output of the activation function, and the input to the activation function is the weighted sum of the inputs plus the bias. Okay. So layers of neural network: input layer, output layer, and the hidden layer. And depending on the number of hidden layers, we can classify the neural network into, say, a single layer neural network, wherein we have one input layer and one output layer. There is no hidden layer. Please observe that. And multi-layer neural network can further be classified into shallow neural network and deep neural network. What is shallow? We have a single hidden layer, but when it comes to deep neural network, we have two or more than that, two or more. So two or more hidden layers, we call it as deep neural network, and we would be concentrating on this because that's the current trend, but evolution of this into deep learning, to be very precise. Okay, so some diagrammatic representation, input layer and the output layer. So single layer neural network, input layer, output layer, and the one hidden layer, so shallow multi-layer neural network. And here we have two hidden layers, so input layer and output layer. So this is deep neural network. Okay, the important thing is, or the basic thing that we come across neural network is the perceptron, right? So here you can see that the weighted sum of the inputs is given along with the bias, and here bias is neglected. So W naught, we can treat it as if neglected, then it will become W1 into X1 plus W2 into X2 and so on up to W into Xn. So here it is 1 if the weighted sum is greater than 0, or otherwise it is -1. So here you can see that the signum function is used as an activation function. The signum, not the sigmoid, signum function. So to make it a simple, so output of the activation function is the final output is equal to 1 or -1. So this is 1 or -1, binary output. So binary classification. So if the weighted sum of the inputs is greater than 0 along with the bias, or if bias is not there, we neglect it, then it is greater than 0, 1, otherwise it is -1. Okay, now to understand or to write the code properly, we need to know how exactly the neural network works. So let's make it very simple. Let's consider now, here we have this is the input layer, okay, and this is the output layer, and say one hidden layer we have. What basically it does, you'll be astonished to know that it's just doing weighted sum just here. Now let's, for time being, to keep our job simple, let us consider a linear activation function. So x is the input, phi of x. So we have this something like y is equal to x, a straight line passing through the origin with slope 1. So let's assume that, I know it's not fair enough to consider a linear activation function because a majority of the applications we use non-linear activation functions, but for the sake of understanding the neural networks better, we will consider the linear activation function. Now see here, now what here, this node, it does nothing, it will just pass. It's just like a buffer. It will allow the inputs to pass through this to the next layer. What we are trying to do here, let's concentrate here. So 3 into 1, so 3 is the weight into 1, 3 into 1, 3 into 1 input, weight into input, plus this is the weight is 1 and input is 2. So 1 into 2 plus the bias is 1, plus the bias is 1. So this is the weighted sum of the input. So here this is V and weighted sum of the inputs. Activation function is anyway linear. So this is the output of the first node itself. Okay, now next, right, say V2. V2 is equal to, again, same thing, just see here. So 2 into 1, so weight into the input, 2 is the weight and 1 is the input, 2 into 1 plus 4 into 2. So 4 into 2 plus the bias is 1. Now what you have just done is you have just calculated the output of the hidden layer. Okay, it's that simple. And when I continue further, say suppose I want to calculate the output of the output layer, then again I do the same process. Please see, observe here, 3 into whatever the output that we get of this node plus 2 into output of this node plus the bias is 1. Similarly for this node, it is 5 into output of this node plus 1 into output of this node plus 1. And whatever we get is nothing but the output. So here we have two outputs, right? So here we have two outputs. So the two outputs are here. Fine. Yeah, let me keep it silent. Just a minute.
Yep. Can you please repeat it?
Oh, okay. Should I repeat these calculations?
Yes, please.
Sorry.
Please.
Yes. Okay, I'll do that. Just a minute. Okay. So now 3, okay, weight into the input, 3 into 1, 3 into 1, plus here 1 weight 1 into 2, 1 into 2, and plus the bias. I'm calculating the output of the first layer, plus 1 is the bias. So 3 plus 2 plus 1. So 3 plus 2, 5, 5 plus 1, 6. Yeah, I hope I'm correct. 6. And let's do the similar calculations here. It is, weight is 2 into 1. So 2 into 1, I'm writing it, 2 into 1 plus 4 into, here, this is the input. So 4 into 2. So 4 into 2 plus the bias 1. So it is 4 to the 8, 8 plus 2, 10 plus 1, 11. So this is nothing but is the output of the first hidden layer, 6, 11, because everything is numbers, 6 and 11. And we continue to do the same thing here also. So for example, here the output is 6, here the output is 11. So what about the activation function? I told you it's a linear activation function. So it is 6 and 11. Here if I have to proceed further again, it is 3 into 6. I hope now you get it. 3 into 6 is 18 plus 2 into 11 is 22 plus 1 is the bias. So 22 plus 18 is 40, 41. Okay, I hope I'm doing the additions correct. Similarly, if I have to proceed, 5 into 6 is 30 plus 1 into 11 is 11. I hope I'm clear. And finally, it is plus 1. So 41 plus 1 is 42. So that's it. It's as simple as that. Now you have done the calculations of in hand without any coding. Practically, you have done it. How you get the output of a neural network, which is having a single input layer, single output layer, and single hidden layer with 2 nodes at each layer, 2 input nodes, 2 nodes at the hidden layer, and 2 output nodes. So all these things I have put here. You have seen it, 6 and 11, which is highlighted here, and here the same thing. I've just written it in the form of a matrix. Now we can write this. These are the weights, and these are the input. So X, and these are the biases. So we get this equation: V is equal to W transpose X plus B. And then I hope you remember 6 and 11 as the output. And then this is a generic formula: weights of the first node, weights of the second node. You can see that whenever I was doing calculating here, if you see here, 3 into 1, weights of the first node, 3, 1. 3, 1. In the first row, we have weights of the first node, and 2, 4. 2, 4. That's the weight of the second node, right? So weights of the first node, weights of the second node, and so on. So we have this. Again, if I continue further, I'll get 41 and 42. What did I get? Yes. I think even have 41 and 42. It's the same thing that is shown here, 41 and 42. And you have completely done in-hand calculations of the single layer neural network. Okay. So let's dive into further and see here. Since I think in the morning session, Boris was telling, if the linear activation function is used, then it is as good as not having a hidden layer, because the entire thing can be brought down to a single input layer and a single output layer with some modifications. So these are the calculations that will reduce it. So the hidden layer is the whole purpose is lost. So that is why we don't go for the linear activation functions. But wherever the understanding is required, there is nothing harm in going for linear activation functions. Fine. Let's understand what is supervised learning of a neural network. Now with diagram, so we have a training data input and correct label, which is given to the input, the neural network, and we get the output for it. So once we have the output, the correct output is also there. The difference is taken, that is the error. Error is fed back to the model, and weight updation happens. What are the weights? Remember the numbers that we had shown here. These are the weights. So initially we do everything in random, and then once we have the errors, we feed back, and then we update the weights. It is that simple. Okay. But how do we do it? Is there any specific learning rule? Because I had told you, right? So depending on the cost function, we will have a learning rule, right? What is that learning rule? Cost function. Usually the sum of the squared errors. That is the objective function, but we'll come back to that later. But for time being, we'll see that, okay, the learning rule that we are using is the delta rule, also called as Adling rule or the Widrow rule, which is also a special case of the gradient descent algorithm. Okay. Fine. So what exactly is that? How is the weight updation happening? The weight updation is happening as per this equation. This is not a general delta rule, but it's a very specific delta rule. Here I can assume that this was for the linear activation functions. So Wij, that is what weight between the ith output node and jth input node. Ith output node and jth input node. This is the weight. This is the weight between the input layer here and the output layer here, is updated using the following rule, which is nothing but alpha into EI into xj. Now what is alpha? Alpha is the learning rate. So it ranges between 0 and 1. And EI is the error. What is the error? Difference between the output and the correct output. DI is nothing but correct output, and YI is the output of the neural network for the random values that we have initialized it. As the time goes on, as we run it again and again, our error should be minimized. Fine. That's it. So this is what is the delta rule. Okay. Now, so let us consider how do we training of a single layer neural network using the delta rule. Okay, and we will try to solve some of the problems that is or linearly separable problems. But before that, let me give a brief overview and then go to the MATLAB part. Okay, so I hope now we know inputs, the weights, bias is neglected for simplicity, and this is the error calculation that is happening. And here the weight updates is as per the delta rule, which was told here. So W11 is nothing but this between this and this. So it is, please remember that delta is proportional to the error. Error, that means at this node because of the input x1. Error at this output node because of the input x2. Error at the output because of the x3 input. So this is how it does. Okay, and this is the algorithm. I can say that it's a pseudocode. Initialize the weight, random values, take the input along with the correct output, because we are talking about the supervised thing, and enter into the neural network and obtain the output, measure the difference. Error is there. Once we know the error, we know how to update the weights. Please remember this diagram. Once we have the error, this error is fed back, weight update should happen. How is the weight update happening? Delta rule. So what is the delta rule? This is the rule. So how do we do it for this particular thing as per these three equations? So we are trying to do that and adjust the weights, repeat these steps for all the training data, and repeat the entire thing until it reaches the acceptable tolerance level. The number of times the training data is entered into the neural network, we call it as an epoch. So if the epoch is more, we are using more and more we are passing the same training data into the neural network to make sure that the output is error is minimized. That means what? We are trying to overfit it. So that should not happen. Okay. Yeah, so here we have told already the epoch and all those things in terms of the block diagram, and we'll just go to the generalized delta rule. But I've told you, right, the linear delta rule is only for the understanding purpose, using the linear activation purpose, because if there is any hidden layer, that would meet the purpose. So we'll go for a generalized delta rule. And what is the slight difference when we talk about the generalized delta rule? Generalized delta rule is like, we'll see what is the difference. Earlier we had alpha into EA into xj, if you remember correctly. It is alpha into EA into xj. But now we have the generalized delta rule where the weight updation is happening as per this particular rule, Wij plus alpha into delta into xj. Now what is this delta I? Delta is nothing but differentiation of the activation function. This, remember, psi prime of Vi. So differentiation of the activation function to error. So use this as an input here and update the weights. That's the only thing. Now say for example, we had used, if you remember, we had used the linear activation function. So x, say y is equal to x. So differentiation of this function with respect to x is 1. So 1 means I'm left out with delta I is equal to EI. Delta I is equal to EI. Which if I substitute back, I'll get Wij is equal to Wij plus alpha into Ei xj, which is same as the delta rule. That is, the delta rule, whatever we had discussed was for linear activation function, but it will be non-linear activation functions. What are the non-linear activation functions? It could be a sigmoid, it could be hyperbolic tan, it could be a signum function, it could be a ReLU. So there are so many types of activation functions, right? So we need to differentiate it, multiply it with the error, you know how to calculate the error, and then that is the delta, substitute back, update the weight. So this is what, you know, say for example, we have used the sigmoid activation function, which is mathematically defined as phi of x is equal to 1 by 1 plus e power minus x. If you differentiate it, I have shown you the steps. If I differentiate it, we get this equation. So please use this because we'll be showing this in the MATLAB code. So this equation, so differentiating this using the chain rule, I can do it, or a differentiation of 1 by x or 1 by f of x, right? So 1 by f of x is minus 1 by f of x square into this thing, right? So I have done this differentiation and we have got it, right? So simplifying this, we have Wij plus alpha into activation function into 1 minus activation function output intoEixj. So this is how the weight update would happen as per the generalized delta rule. The equations are simple, okay? Now, so what is stochastic gradient descent? Without going to the mathematics, stochastic gradient descent is nothing but for every training data, whatever I have the training data, I will get certain output, I'll do the update, weight updation would happen. So if there are 1000 data points, then the weight updation would happen 1000 times, okay? So it is quick, but the thing is that it may not be stable. It may wander around the solution point. The other thing is batch, that is, okay, let the weight updation happen intermediately, I'll get some output, but I'll take the average of the weight updates and then update it finally. This is what we have it. So this is called as batch method. But in case of deep learning, whatever we have these days, they go for mini batch. That is, divide the entire training data into some batches, small batches, take the individual weight updation, obtain the average, update it, repeat the process and continue it. Okay, so suppose I have 100 training data points and it is divided into 20 mini batches. So there are 5 mini batches. So there it would happen 5 updations or 5 weight adjustments would happen. Okay. So with this, let's go to a typical problem. Okay, now here is nothing but the input, and the one which is there in the bold is the output. Okay, the one which is in the bold is the output. So 001, 011, 101, 111. But if you see the third dimension, 11111, it's the same thing. So z plane is 1. So we'll neglect it for better visualization and we'll represent this data on a 2-dimensional point, and the output is 0011. So if I do that, so it is x, y. So remember 0001, 1011. Okay. So 00, 01, 1011. For that, what was the output? 00 for first two, 00, and 11 for the next thing. And you can see that this is the x, this is the y. Remember, usually they show in terms of triangles, circles, all those things, and then they try to classify it. Here I have shown you with numbers. And how do we separate this? How do we classify this? That's what is the objective. Remember, we are using the generalized delta rule. So delta is nothing but a differentiation of the activation function into EI. We will use the sigmoid activation function. So sigmoid activation function, if I use sigmoid activation function into 1 minus sigmoid activation function output into EI, and weight updation is this, and this is how it finally updates. So let's go to the MATLAB and then try to solve some of the numerical problems. First we will try to solve this, then we will try to solve the OR problem, AND problem, and so on. Okay. Discard. Okay. Okay. So is the MATLAB screen visible to you all?
Yes, sir.
Okay. So yeah. So let me do it with the stochastic gradient descent. Yeah. So okay. Now, sir, why we have taken the input? So clear on input. Input is, remember, 001, 011, 101, 111. If you see this, 001, 011, 101, 111, or 0001, 1011. Okay. 0, 0, 0, 1, 1, 0, 1, 1. What is the correct output we have? Let me go for this. 0, 0, 1, 1, right? So 0, 0, 1, 1 is the output. So which is represented by D. Okay. Now, what is the first step we have? First step we have is, let me go to the pseudocode. Then it will be easy for you to understand. Yeah. Okay. Yeah. Yes. Okay, so initialize the weight at adequate values, right? So I'm initializing the weight with adequate values. So random values. So randomly I've just taken random values. Okay, so 1 row, 3 columns. So random, I really have initialized. Then I'll pass this data points. These are the data points. It's a supervised. Remember, it's a supervised one. So this is the input. This is the correct output. Okay, and I'll pass this points 1000 times. So epoch, remember I told you, right, number of times the training data enters the neural network. So that's the epoch. So 10,000 times. So I'll train it. So this is the function. What am I passing? The weights, the initialized weight, the input, and the correct output. Okay, I'm passing to it. So once it runs 10,000 times, the W will be updated. So how is the update happening? Remember I told you, it takes the input, correct output, along with the initialized weights, random weights. Updates would happen as per this rule, and alpha into delta into xj. Weight updation is happening, and this we repeat for all training data and until it reaches. So instead of reaching to a specific level, we have restricted ourselves to the number of times we are training the data. Right now, yeah, please observe this, how exactly we are doing this. 1 second. Yeah. So here, if you see that here it's a weighted sum of the inputs. There is no bias. Output is nothing but function of the activation function. So if I have to write it, so here for this particular thing, it is W1 into X1 plus W2 into X2 plus W3 into X3. Okay, so this is V, and we are passing this through an activation function. So activation function is sigmoid. So final output Y is sigmoid. So sigmoid is the function. Sigmoid of V. So sigmoid of V. So that's it. If you know this, you can directly go for the MATLAB. So let me just go now. This card. Yeah. So X is the input, and V is equal to weighted sum of the inputs. Remember, in terms of matrix notation, weighted sum of the inputs, and output is the sigmoid of V. So we have got it. So updated weight, we have judged this, and we have trained it. But let me go into this. What is there inside this? That is, we are using the delta rule and stochastic gradient descent method. So weight updation would happen every time. Okay. So let me go to that. So yeah, stochastic gradient descent, right? So let me go to this particular function. I've opened it. So the input is the weight, the input and the data. Alpha, remember the learning rule, and we have number of inputs is only the 4, 0, 0, 0, 1, 1, 0, 1, 1. Okay, the Z parameter is same, so I'm neglecting it. And for all the set of input, take the input, take the correct output, corresponding output to it, and V is equal to W into X. So I'm trying to implement this, right? So let me go back to the basic diagram of any neural network that is shown. Okay, I think this is better, or yeah, just a minute. Yeah, okay, so this would be better. So input I have, so you are passing that input to this neural network, right? So that we are trying to do, whatever we input we have, the correct output we have, input is passed into the neural network, weighted sum of the inputs, given to the sigmoid function, output is calculated with random weights. Remember, the weights were random, initialized. Okay, now we have this. Let's go to the diagram again. We'll measure the output. What is the output? Difference between the output and the correct output, right? Difference between the output. This is the correct output. D is the correct output. Y is the output of the neural network for this particular values of W. So we have got it. And delta is what? Sigmoid function into 1 minus sigmoid function into E. If you remember the equation just now, we said that, right? For sigmoid activation function, this is what we have. Okay, let me show a simpler one. Yeah, activation function 1 minus activation function into error, right? So we have that, and this is what is the delta. Once we have this, the delta W is updated, the delta rule, and for everything, all the weights are updated. How many weights are there? If you see the diagram, this is a neural network under consideration. 3 weights are there, W1, W2, W3. Initially, it was random. Now we have got some output. We have measured the error and we have updated the weight using the delta rule. I hope you have understood it. So using the delta rule, we have updated it, and this is the updation. Again, this function is called 10,000. I'm so sorry. Yeah, 10,000 times. So for this, we get the corresponding output. Now let me run. So Sigmoid. So let me run the stochastic gradient descent. Yeah, run. So change folder. Yeah. Okay. Okay. Now let me show you what exactly. Let me undock it. Then it will be better. Yeah. So I've undocked it. You can see that the output is, this is 0.01, which is close to 0, 0.00, which is close to 0, and 0.99, which is close to 1, 0.99, which is close to 1. Remember what was the output? 0011, right? And we have got the output 0.01, 0.0083, 0.99, 0.99. So we have solved this problem and we have classified the output for these inputs itself. So our training data itself is the input. Okay. So where is the validation? No, it's very simple. For the demonstration purpose, I'm trying to use it, and we have solved this problem. And this is what is the classification. So first one belongs to one class, the other one belongs to another class. It's a linearly separable problem because we can use the straight line itself to get into 2 categories. Fine. So we have solved an important problem here. Let me go for an OR problem. What is OR problem? Again, the same thing, x1, x2, x3. When either of the inputs is 1, output is 1. Okay. So here 0, 0, we'll neglect this x3 for time being. Okay. We'll neglect this and we are projecting it onto the 2 dimension. Okay. So this is 3-dimensional data. We are projecting it. So we are neglecting for time being this one. Here both the inputs are 0, output is 0. Either of the input is 1, output is 1. Either of the input is 1, output is 1. Both the inputs are 1, output is 1. So we have plotted the points 0, 0, 0, 1, 1, 0, 1, 1. And we are calling this particular one, whichever is belonging to 1, as class A. These are the class A. And this is class B. Okay. And we want to check whether the same neural network, will it be able to solve now the OR problem. So let me go back. So what is the correct output now? 0 followed by 3 ones. 0 followed by 3 ones. 0 followed by 3 ones. Now let me run it, the stochastic gradient descent. And now we should get the output as 0 followed by 3 ones, very close to it. You can see that I have run again. So 0, this is 0, this is 1 because 0.9892 is 1, 0.982 is 1, 1 is 1. So this is classified as 0 group, this is classified as 1 group. So we have again done a binary classification and we have successfully solved an OR problem using a single layer neural network. This was the figure, right? This was the neural network that we had used. Using this, we have solved this. We can also solve an AND problem also. So this is an AND problem. Again, we'll neglect this and we'll project this data onto the 2-dimensional. 0 if only when both the inputs are 1, output is 1. So here you can see this one, rest all is 0. We'll call this as class A, remaining as class B. So this is class A because only when both the inputs are 1, it is class A. Remaining thing is class B. We want to check whether it is linearly separable problem or not. We'll use again the same neural network to solve even the AND problem. Okay, AND problem. So let me go to the demo. Now as per this, it is 3 zeros and 1, right? So 3 zeros and 1. 3 zeros and okay. So 3 zeros and 1. Let me run it. So if I run it, okay, so I've got the output. Yeah. So 4 outputs we have got is 0 because 6.4 into 10 power minus 6 is very close to 0. 0.0173 is 0. 0.0173 is 0. But you see here 0.9796. So the input data is categorized. These 3 is one class. This is one class. That is what we wanted, right? The first 3 data is one class, class B. The other one is class A. So we could also solve an AND problem, which was again a linearly separable problem using the same neural network. Now let me try to solve another interesting problem called as XOR problem. Again, we are neglecting this and we can project it onto the 2-dimension, and the output is 0, 1, 1, 0. This combination remains the same. Only if, for different inputs, output is 1. Okay, 0, 1, 1, 1, 0, 1. Okay, so let me try to solve that problem using a neural network. Okay, so fine. So 0, 1 is 1, 0, 1 is 1, and 1, 1 is 0. Yeah. So let me try to check whether we will be able to solve it or not. Okay, so let me have run it. We have got the output. So the output should be 0, 1, 1, 0, right? 0, 1, 1, 0. Let me check what do we get. This is 0.5, 0.5, very close to 0.5, very close to 0.5. What was the actual output supposed to be? The output was supposed to be 0, 1, 1, 0, but it failed. Why did it fail? We could solve AND problem, we could solve OR problem, we could solve any other problems could have been solved, but the XOR problem was not solved using this single layer neural network. What was the issue? Let's project this onto the diagram. Okay, we know that 0, yeah, right? 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, 1, 1 is 0, right? So if I project this, this and this belongs to one class, this and this belongs to one class, right? So we have BAA, BA, AB, right? So 0, 0 is B. So 0, 0 is B. Okay, 1, 1 is B. 0, 1 is A. 1, 0 is A. So this class, or in terms of numbers, right? So we have this, but a straight line couldn't solve it. But we want something like this. This is one particular class, and this is another particular class. So XOR is linearly inseparable problem, and a single layer neural network cannot solve this problem. Okay, so seems interesting. Instead of just showing it in terms of these things, that is all this diagram, and then fitting a model for this, we have used an actual numbers and solved very interesting, and I know it's very initial level, but we want everyone to come at the same level. So we have solved AND problem, OR problem, a typical problem, generic problem, and an XOR problem, which couldn't be solved by a neural network, single layer neural network. That brings to the question, okay, but practically if you see, most of the problems would be linearly inseparable problems. That means I cannot go further. That is, I have only single layer neural network, and I cannot, let me just a minute. Yeah. So I was talking here, and I cannot solve this kind of problems using single layer neural network. So then what thought would have come? The thought would have come is that we would go for multi-layer neural network. Multi-layer. That's how the multi-layer neural network was originated. But the real problem was, remember how the single layer neural network training actually happened? If you remember, the single layer neural network training actually happened in this way, right? Initialize the weight, give the input, obtain the output, calculate the error. Error is only known for the output layer, okay? And then update the weight, repeat it for all input, repeat the entire set again. That's how it was done. But when it comes to multi-layer, that means what? I'm introducing an hidden layer. When it comes to hidden layer, do we know what is the output? What is the correct output here? Do I know what is the correct output here? I know the correct output here. So input and correct output, because it is a supervised thing. I have the data set as input, comma, correct output. Final output I know. What is the final output? I know. But do I know intermediate outputs? Do I know intermediate outputs?
No.
No, I do not know. So that's how the development of neural network was stopped. I think nearly 3 decades, 3 to 4 decades. Then in late 1980s, the backpropagation algorithm was proposed, wherein it was proposed how to define the errors in the hidden layer. So a solution was proposed how to define error in the intermediate layers. Once we know the errors in the intermediate layers, we can calculate the deltas. Using the deltas, we can update the weights, and that's how we can train the entire neural network, and we got the multi-layer neural network. I hope you have understood the motivation from single layer to. And by the way, before going further, I just wanted to show the batch method and this thing. Just a minute. I'm so sorry. Yeah, let's go here. The same problems also can be solved with the batch method, right? Here I had used the stochastic gradient descent, but the batch method treat entire thing as a whole. If you see it, this is the input, it's the output. So this is the OR problem. In randomize the weight, pass the data 40,000 times, delta batch, call the delta batch. What is there in delta batch? That's the only difference. Okay, now just check here. Alpha, the learning rate. The initial delta W's are made it as 0 because we calculate the sum of all the errors. Now see here, the input and the correct output. V is nothing but the weighted sum of the inputs. The correct output of the neural or the output of the neural network is interpreted through the sigmoid function. We have calculated the error and we have calculated the delta. Okay, so delta is nothing but sigmoid function into 1 minus sigmoid function into error. As per that equation, right? We have calculated delta. Now we are just making it as delta W. So we have done it. Okay, for this particular input, what is the output and what is the error that we have got? We have made it as delta W. We don't update it immediately. We try to sum everything. So once all the input is done, we have got the sum, total sum of all the errors. Sum of all the errors. Once we do that, divided by n, number of n. So we do it. Remember this particular equation, what we said. So we do it depending on the number of data points that we have. We have done it. So that we have obtained the delta W. So once the delta W is, now the weight updation is happening. That's the only difference. Weight updation is happening. Here, the weight updation was immediate. If you see here, the weight updation was immediate, says here. But here it is sum, averaged, and then the average weight is updated. That's the only difference. And also we have earlier we had run for 10,000 times, but we had now here we are running it for 40,000 times. So but we would get the output. This is the AND problem, sorry, OR problem, right? Because 0 0 0, rest all everything is 1. So it is an OR problem. If I run it, I should get 0 1 1 1, right? So I think I would have got the output. Yeah, so 0 1 1 1. So it has correctly classified it. Again, see, single layer neural network using the batch method also has solved the problem. Then what is the difference? Let me try to run that. If I try to run that, then you know, visualize it. What is the difference between the stochastic gradient descent and the batch method? So x-axis represents the epoch, that is number of times the data training data is passed into the neural network, and this is a training error. Our objective is to make sure that the error minimizes it, right? So you can see that for the epoch very close to that of 400 itself, the training error is becoming very close to 0. But in terms of the batch method, you can see that even after 1,000 points, we are not getting that performance. So that's how it is. If I again run this, let's see what happens. You'll get another curve over it. And because everything is random, right? Now see here, again for this particular thing, you can see that it is overlapping it, and you can see that how it has performed. For because it's random, right? Weights are random. Again, it has tried to converge, but you can see that even for if I run many times, also you can see that the stochastic gradient descent has already made error very close to 0, but here it is still not, even for the 1,000 epochs. So that is why we would go for the stochastic gradient descent. But if the number of data points is more, it wanders around the solution. So mini batch is the trade-off between these two things. Okay, so yeah, let's. Okay, it has now finally opened it. Okay, so this was the online that I was talking about, using the I think the Jyoti Prakash sir had sent, right? Using that, I have created it. So if I want to create something just similar way, you can just do it. New script. So I can do it. Type the code, save it. So if I want to save it, say save as. So test. So test.m. So test.m. We've got it, so we can do it like this and then run it. So remaining steps. So I have run the XOR problem, say XOR problem. Let's try to run that XOR problem, whatever we just now showed. So if I run this, I'm so sorry, I should have run this. Yeah. So let's see this now XOR problem using that single layer neural network online, and we could see that it should have output was supposed to be 0 1 1 0, right here 0 1 1 0, but we are getting 0.5 very close to 0.5. So we couldn't solve the XOR problem using the single layer neural network because it was not a linearly separable problem. You would go for the multi-layer neural network. But the problem was that in the back propagation, the error is not defined in the hidden layers. So using the in multi-layer neural network, we don't know what is the error in the hidden layer, and that problem was solved by the back propagation algorithm, wherein the error was a specific method was given how to calculate the error for the hidden layers. And the solution is that the in hidden layer, in the back propagation algorithm, the error would propagate in the backward direction. That is, error is calculated as a weighted sum of the deltas. Okay, we'll see that very shortly. But let me take again a simple example and do hand calculations and then go for the MATLAB implementation. Okay. So this is the back propagation algorithm. Again, we are taking the same network that we had considered earlier. So here we have, okay, so this is the input layer, and here is the output layer, and here we have the hidden layer, right? So hidden layer we have, and now instead of taking linear activation function, we will take a non-linear activation function, and we will take the sigmoid as the non-linear activation function. So one of the widely used non-linear activation functions. So sigmoid we'll use. So definitely hidden layer is there. So we know how to calculate the error. So let's see how the calculations would happen. Okay. So we know that now here is nothing but, if I want to calculate the output of the first node, it is W11 into X1 plus W121 into X2, right? That's the first row. W111 into X1 plus W121 into X2, right? Plus, so for this particular thing, this into this, that is X1, plus this into this. Okay, so W22 into X2. This is what we have. Bias is neglected for convenience, right? So we have that. If you see that now, you have it W21 to the 1 and W2 into X2. So we have got it. So this is the output of the first hidden layer. So this is node 1 and node 2 of the hidden layer. What is the output of the hidden layer? This is weighted sum of the inputs. It will go through an activation function, and the activation function that we are using is the sigmoid activation function. So output is nothing but this is the first output of the hidden layer node, and this is the second output of the hidden layer after passing it through an activation function. This is just the weighted sum of the inputs, okay? And then through an activation function, we get first output. Through activation function, the second output. So we have done this. Inside this itself, we assume that there's an activation function, weighted sum of the inputs, activation function, output. Okay, so we get it. And here is nothing but the y1 and 1. And here it is nothing but the y2 and 1. The superscript indicates the first hidden layer, okay, or the first layer that we are coming across when we are moving from input to the output. Okay, so we've got this. Similarly, in the later part also, we can do the same thing. That is, here if I want to calculate, it is W112 into Y11 plus W122 into Y2. So this is what we get. Please here, W122, W122, Y1, Y2. And similarly, V2 also, we do the same way, right? And then we have calculated the weighted sum of the inputs. Inputs means output of this layer here. And then pass it through an activation function. So activation functions are there. So we have got the final output. So this represents the final output or output of output layers. Output node 1 output layer, node 2 output layer. So we have got the outputs. Fine. So we know calculate the error also. Error also we know because we know the correct output. So error 1 is nothing but D1 minus Y1. Error 2 is nothing but D2 minus Y2. That also we know. And we'll be using the generalized delta rule for the weight updation process. So delta is nothing but we know that delta is nothing but differentiation of the activation function, differentiation of the activation function into the error. error, right? So that we have to do it. So delta 1 is nothing but, we know that differentiation of the activation function into E1. Delta 2 is nothing but differentiation of the activation function into E2. So we have done these calculations. Now error, we have to know that how is the error calculated at the hidden layer, right? So here in the back propagation algorithm, the error of the node is defined as weighted sum of the back propagated deltas from the layer on the immediate right. So here whatever we have got, weighted sum of the deltas, we will do it. That is nothing but the error. That itself is the solution. I repeat. Now say, suppose here error is nothing but difference between the output of the neural network and the correct output. Correct. Here what do we do? Error, how is it calculated? W112 into delta 1 plus W212 into delta 2. So here we have calculated now the output layer of this one, this particular node. Suppose I want to calculate again here error, it is W122 into delta plus W22 to the power 2 into delta 2. So it is nothing but weighted sum of the deltas. How do I calculate here? Again, I have to do it in the same way. W11 into 1, delta 1 to the power 1 plus W21 to the power 1 into delta 2 1. So we have calculated error. Similarly, we repeat it for this process. Putting everything in terms of a matrix notation, whatever I've just now told, we get these equations. So error 1, that's what I had told now. W1, this into this plus this into this. So this equation we have now. And deltas is nothing but again differentiation of the activation function into the error. We have got the error, so we can calculate the deltas. Similarly, we have calculated the error across the first hidden layer, second node. This is first node, this is second node, first node, and this is the second node. We have calculated again. So here we used to calculate output is nothing but this is weighted sum of the inputs through the activation function. Okay, this is what in the forward process. In the backward process, it is the error. Error is propagating in the backward direction. Error, how do we calculate? Error into differentiation of the activation function is delta. So we are calculating this. So using the same thing. So representing everything in terms of matrix notation, we would see this. So we have got error as nothing but weighted sum of the deltas. Once we have the errors, we can do the weight updation using the generalized delta rule itself. Say for example, what is the generalized delta rule? Alpha into delta into Xor. Remember, this is the delta. Delta is nothing but differentiation of the activation function into the error. So once we do that, the weight updation happens. And now here you can see that how do I proceed practically. If I have to show it, it is the weight updation. What happens? Weight updation plus alpha into delta 2 into y1. So if I am doing the weight updation between W21 means second output node and the first input node. First one represents output, second one represents the input node. So second output node and the first input node. It means with respect to this layers, okay? So to the power 2. So I'm trying to do this. How do I do that? So W21 plus 2 alpha into, again you see that it is proportional to delta and the input layer. So here, so this delta 2 into E1. So you see that it is the same principle. Whatever we said earlier, it is the same thing implemented. It is the same equations. Only thing is the error calculations has varied for the intermediate purpose. So here also, if I try to update the weight for this particular thing, which is between input and the hidden layer, it is W11 means first output layer, first input layer, right? It is nothing but alpha into delta 1 of 1 into x1. So you can see that alpha into delta 1 of x1. So it's the same principle that we had discussed for the delta rule. So the back propagation algorithm works in this fashion. So let me write a pseudocode so that it will be easy for us to understand the MATLAB code. So randomly initialize the weight, pass the input to the neural network, obtain the output, calculate the error, calculate the delta, differentiation of activation function into error. Now we want to calculate the error of the intermediate nodes. Error is nothing but of the intermediate nodes is nothing but hidden layers. Weighted sum of the deltas, done. And delta of the intermediate layer is nothing but again differentiation of the activation function into error. This is done. And repeat this for all the training data and repeat the entire step for the number of epochs until you make sure that the error is reduced. Okay, let's see this how with this simple back propagation algorithm we can solve the Xor problem, which was a linearly inseparable problem. Using single layer network we could not solve it, but using the multi-layer neural network we would be able to solve it. So here we have we are considering this neural network. So this is the input layer, this is the input layer, and this is the output layer. There is only one node, and here there are 3 nodes. Why there are one node? Because the output is binary, either 0 or 1. Okay, that's why we have only output. Why 3 inputs? Because there are 3 inputs, x1, x2, x3. That's why we have 3 input nodes, and one hidden layer. We have one hidden layer. This is the hidden layer, and the activation function that we use is the sigmoid activation function we use, and we see how we can solve the XOR problem using this. Okay, so let me go back to the MATLAB code. Okay, so graphically we are trying to represent this. We know that these two belongs to class A, the other one belongs to class B. So class A, class B, let's try to solve this. So the visual representation, of course, neglecting the third dimension, we have written this. So let me go to the MATLAB, and yeah. So let me go to the MATLAB. Okay, so let me go to it, and yeah, now so let me go to the diagram so it will be easy for you to understand. Yeah, this is the input 001. Okay, 0001 1011, rest all is 1. Okay, 0001 1011, 4 inputs, this everything is 1. Okay, and the correct outputs are, what are the correct outputs? 0110. So 0110. Fine. We have to random. Now there are 2 weights. One, the weights between the input layer and the hidden layer, and another set of weights between the hidden layer and the output layer. Correct. So inputs between the here. So W1 represents the weight between the input and the hidden layer. W2 represents the weight between the hidden layer and the output layer. Okay. Now we have randomly initialized the weight. Remember the first step we have done. Randomly initialize the weight, pass the input, correct output to the neural network, calculate the output. Correct. So we'll pass this data, weights randomly initialized. We have to train the neural network, input and the correct output. This is training part, this is validation part. Okay, so we have to train it. We have given this as an input. Let's go to backdrop XOR. So backdrop XOR. Fine. So we have passed it, input, weights, random initialized weights, input and correct output, learning rate 0.9, and we have got, so the input, the correct output. Okay, now what is this according to this diagram? So weighted sum of the inputs is the first calculation, right, that we have to do. So here weighted sum of the inputs we have done, and we are using sigmoid activation function as I have told. So the output of the hidden layer is nothing but passing the weighted sum of the inputs through sigmoid activation function. So this is the sigmoid activation function. So the weighted sum of the input is passed through sigmoid activation function, and we have calculated the output. So this is the output of the hidden layer. And then what we have to do, we have to pass this to the output layer, right? Again, weighted sum of the inputs, then sigmoid activation function, and then a final output. So weighted sum of the inputs is nothing but now the output of hidden layers, and then we are passing it to the sigmoid. We have got the outputs. Now we'll try to calculate the error. The next step is the error. So error we will calculate. Once we have calculated the error at the output node, so let's go to this step so it will be easy for you as per this code. So we'll calculate the error. So error calculation is done. Error calculation is done. Delta we have to do. Sigmoid function is nothing but differentiation of sigmoid activation function is nothing but sigmoid function into 1 minus output of sigmoid function into the error. So output of, so we have done this. So we have calculated delta, and then now we have to do back propagation, right? Because we also need to calculate the errors of hidden layers. So how many hidden layers are there? As per this diagram, there is only one hidden layer. So we'll go back and we'll do this. What is error? Weighted sum of the deltas. So weighted sum of the deltas. So weighted sum of the deltas. And then how is delta calculated as per the equation? Delta is nothing but differentiation of the activation function into error. So output of activation function into 1 minus output of activation function into the error. So we have calculated the error, that is this particular this thing. Next, weight updation will happen as per the generalized delta rule, because it's a stochastic gradient descent that we have used. And weight updation, this is between input and hidden layer. This is between hidden layer and the output layer. And this we repeat it for all the data, and we call this function many number of times. Okay, so we do this. Once we do this, so we have repeated it and repeat everything. So as per this rule only we have done it. So once we do this, let me run this now. Let me test it. Now we have to validate it. So for the validation, we are giving the same input. Okay, and we are calculating what is this thing, weighted sum of the inputs through the sigmoid function, the first outputs, that is intermediate layer outputs, hidden layer, and then weighted sum of the hidden layer outputs, and then through the sigmoid function we get the final output. Okay, so let me run it and just check whether the Xor problem is solved or not. So what should be the output? 0, 1, 1, 0. Remember? So 0, 1, 1, 0. Okay, so we have run this. This is 0. This is 1. This is 1. And this is, why are we getting 0.5? It should have been close to 0. Just a minute. Let me rerun again. 1 second. This is backdrop Xor. Yeah, okay. And so let me show it. Yeah. So sorry. Yeah. Yeah. So we have run twice. So this is 0, 1, 1, and 0. Okay. So we have run twice and we have got the correct output. So 0, 1, 1, 0. So it classified correctly. So yeah. So we have done it. And we could classify, so using this neural network, that is one hidden layer itself, we could solve a problem which was linearly inseparable using the, this is called as multi-layer neural network, but to be very specific, this is a shallow neural network using nonlinear activation function, input layer, output layer, one hidden layer, we could solve the Xor problem. Okay. So we have solved it, right? So is the sessions interesting, or am I fast, or is that okay? Give the link for Momita. I think the Jyotibra sir has already shared those details in the Google Classroom itself.
What?
The link for the online version of MATLAB is already put up in the Google Classroom.
Okay, sir. Thank you.
Okay. Okay. Here also its link is already provided. Yeah. Fine. Yeah. Sure. Okay. So let's go to do some image processing application problems. With this, let's see how we can. So till now we were trying to solve only two class problems. Two class means binary class problem, either 0 or 1. So let's try to see how we will solve a multi-class problem, and we'll see. Okay, let's go. Okay, so before that, let me introduce. I remember I told you that depending on the objective function or the loss function or the cost function, the learning rule is decided. The two widely used, the cost functions, are the mean square error, what Bora sir was talking about. That is error, that is correct output, and output of neural network. Error is squared, and then the sum. So here the error, so mean some of the squared errors, and then other one is the cross entropy. The cross entropy, it looks like a complicated equation, but if I try to split it, say for example for a two-class problem, that is either 0 or 1, right? So if I try to split it, we will have this particular equations. But before that, let me comment on the some of the squared error problems. So say for example, this is the cost function that we have. We always try to minimize it. So this is the error that we have, difference between the correct output and the output of the neural network. If it is very close to zero, that means what? If a neural network is properly trained and if the difference is zero, that is error is zero, then the cost function is also zero. But if the error increases, the cost function is also increasing. So the cost function is directly proportional to the error. So the greater the difference between the output and the correct output, the larger the error. So it is clearly noticeable that the cost function's value is proportional to error. So cost function is proportional to error. Now another thing that we have is the cross entropy function. Say for a 2-class problem, to keep it very simple, let's separate this. So here we have the natural log of y into d. Say if d is 1, we would say that the cost function would be proportional to this, and if d is 0, then it is natural log of 1 minus y. Now let's see whether it follows the same way. The same way means, in the sense, if the error between the correct output and the output of the neural network is minimized, the cost function is minimized. Otherwise, the cost function is becoming more and more. Or that is, in other words, cost function is directly proportional to the error. That is what is all about. Okay. Let's try to see that. Say for example, now remember we had said that this for d is equal to 1, we have natural log of y, right? So x-axis is the output of the neural network, and say y we have the cost function that we have. So if d is equal to 1, d is equal to 1 means correct output is 1. Correct output is 1. Neural network output is also 1. So what is 1 here, right? So what is natural log of 1? 0. So the cost function has become 0. So error is 0, cost function is also 0. Now say, suppose the correct output is 1, but the neural network has shown it as 0. 0. What is natural log of 0? Undefined, but say let's infinity. That is very high value we get. Very high value we get as the error is becoming very close to 0. So the error is high. So that means what? The cost function is proportional to error, even in this case. The other one, that is, if d is equal to 0, we have that it satisfies this particular equation, right? Natural log of 1 minus y. Let's see that. So the correct output is 0, and say neural network output is also 0. So neural network output is 0. What is the difference? 0. So error is 0. So the cost function also should be 0, right? Let's check that. 0. Substitute that y is equal to 0, right? Substitute y is equal to 0 here. So y is equal to 0. If I substitute here, natural log of 1 minus 0. Natural log of 1 minus 0 is natural log of 1. Natural log of 1 is 0. So error is 0. So the cost function is also 0 when the error is 0. Let's see. The correct output now is 0. But the neural network output gave it as 1. 1. Okay. So 1 it is giving. 1 minus 1 is 0. So that means what? It is a very high value. So the cost function is directly proportional to the error. Usually in the deep learning, whatever the current is used, the cost entropy function is the objective functions that is widely used. And accordingly, there is some slight changes in the how the weight updation would happen. First step remains same. That is, initialize the neural network with adequate values. Fine. That is same thing. Now give the input, correct output, calculate the neural network output. Fine. That is also fine. Error is also difference between d and y. Now delta is equal to e. Delta is not equal to differentiation of the activation function. Differentiation of the activation function into error. No, it is not. It is not. It is e. It is as simple as that. This is delta. Okay. So it is as simple as that. And propagate this backward. Error is weighted sum of the deltas. Here delta, this is at the output I'm talking. In the intermediate, now the delta is equal to differentiation of the activation function into error. So by doing this, you may think that it is very simple, what we are neglecting it. Earlier it was already there, but this has brought a tremendous increase in the performance. I'm not going into the mathematical proofs of it, but we are just telling that yes, because of this one small thing, it has got the performance has improved. Okay. Yeah, so the deep learning employs the cross entropy driven learning rules. Okay, because of their superior learning rate and the performance. Okay, now so we will just see whatever we have learned now for this entropy functions. So here we have, say we have the deep neural network. So the input layer, hidden layers, output layers. Error is calculated. That is, error is nothing but difference between, this is the second node, right? Difference between the correct output, this is the correct output, and the output of the neural network. This is fine, error. And what is delta here? Delta is nothing but, delta is same as EI. So remember, that's the change. Now we'll propagate the error backwards. So how is the error calculated here? Weighted sum of the deltas. So all that is done. Weighted sum of the delta. This is given as an input to the activation function. So how is delta calculated here? Delta is nothing but differentiation of the activation function into error. So that's how the deltas are calculated at the hidden layers. Here the delta is calculated as delta same as the error. Okay. So that's the major difference. So using this, just a minute. Let me go to the, okay. So the cross entropy function. So using this again, we can check the XOR problem is solved. We will run this. So superior learning rate, better performance. So we have run it. Let's check the output. Yeah, back propagation. Now you can see that very close to 0, very close to 1, very close to 1, very close to 0. See the values. Okay, you can see that learning rate is fast, performance is better. And to prove that, say, let me run the code here. The same thing, I have the same other problems to calculate how the training error decays. So let me try to run this simple code and let to get the output. Just a minute. Let me close everything and run again. It's got it now, closed everything. Let me run it. Yeah. So this is based on the cross entropy function and the sum of the squared error, the different which decides the learning rule. So here, the one in the blue dots, you can see that after epoch 300 or 400, the error, the average of the training error is becoming 0. So here you can see that. Yeah, very close to that. But whereas when it comes to the cross entropy, let me show it here. Yeah, some value. I think I have to stay for some while. Yeah, so for 39 epoch itself, the error, you can see it as very close to 0. So that's how the cross entropy function is better compared to the sum of squared error. Not only that, any problem you can take. Say, suppose now I change this to an XOR problem. XOR problem also, earlier was a linearly separable problem. Now it's a linearly inseparable problem. If I try to run it, I should have closed it. I'm sorry for, yeah, I think, okay, but I had not used multi-layer neural network. So that's the thing. So that's why the error was not solved. Okay, I should have used this thing. Yeah. Otherwise, you can always see that I had used the normal this thing. Okay. So that's why the error didn't this thing, and both the error was exploiting. Okay, so you should have used that. Okay. So with that, let us go to the multi-class classification. But what is the summary now? So a multi-layer neural network would solve this problem. Okay. But when it comes to a single layer neural network, it cannot solve a linearly inseparable problem. Okay, let's go to the multi-class classification. Say, suppose I have this. 3 classes, say class A, class B, class C. I need to classify it. So it's now a multi-class problem. Given an input data, I should say whether it belongs to a circle, triangle, or a square. But how do I formulate it? Say, for example, the input data, the coordinates. These are all the coordinates, right? X-axis and Y-axis, and the coordinates. So these are the coordinates, and this belong to particular class, class 1, class 2, class 3, and so on. And let me say that I have this particular neural network, so configured neural network for this particular class. So that 2 inputs are there, so 2 input nodes, and 3 outputs is required, so 3 output layers. Earlier it was only 1 output layer because it was a binary class problem. Now it's a multi-class problem, so 3 outputs are there, either class 1, class 2, or class 3. We would formulate like this. And next, instead of that, we will have to bring everything in terms of numbers. So class 1 means 100, class 2 means 010. We will try to encode it. And class 3 is 001. So this kind of, say, having the number of output nodes equal to the number of classes is called as the one hot encoding or one off encoding technique. So now see here, this is the input, these are the correct outputs. So 100, class 3, class 2, class 3. The same thing is now formulated in this particular fashion, everything in terms of the numbers. So input layer, the output layer, number of output layers equal to the number of outputs, class 1, class 2, class 3. Okay. But and also whenever it is a multi-class problem, it is advisable to use a softmax function at the output node, that is softmax activation function at the output, compared to the sigmoid activation functions or the other activation functions. The reason is that because the softmax function not only consider the weighted sum of the input that is given to it, but also it considers what was given to the other. Say for example, I have the weighted sum of the input as 2, 1.1. So what the softmax activation function is this? This is the mathematical model, but to keep it simple, I've just put it in numbers. So the output of activation function will be like this. So e to the power 2 by e to the power 2 plus e to the power 1 plus e to the power 0.1. It will calculate it. So you'll get this number. Now, again, if you have to do this, e to the power 1 divided by e to the power 2 plus e to the power 1 plus e to the power 0.1. So it does this, do this calculations. Now you can see that it is considering the weighted sum of the inputs of all the nodes. Here there are 3 classes, so it is doing to all. And when you sum all these things, it will be close to 1. So the probability is always equal to 1 when I sum these things. So that's the advantage that I get. And also I would get the what the weighted sum of input is going to the other output nodes. But when it comes to the sigmoid, we never bother what is the weighted sum of the input that is going at the other node when we are trying to decide the final output. But that is not the case in case of a multi-class classification problem. So what would be the general pseudocode that would be there? We will see a specific example, but I'm just talking about the generic. Again, just see the training steps are exactly the same thing. Construct the output nodes to have the same value as the number of classes. So if it is 3, then 3 output nodes are there. And softmax output is used as an activation function at the output, right? And we turn the classes into numerical vectors. So 1, 0, 0, 0, 1, 0, 0, 0, 1 that we did now recently. Once we have done these two, remaining steps is exactly the same thing. That is, initialize the weights with the adequate values randomly, calculate the error. So correct output minus output of neural network, and delta is equal to E. Remember the cross entropy function that we are using? This is at the output node. Next, for the intermediate layers, error is nothing but weighted sum of the deltas, and delta is nothing but differentiation of the activation function into the error. And repeat this for all the training data, and then rerun with the different training data. And once you've got this, the weights update will happen like this using the stochastic gradient descent in the once this is done. So alpha into delta into xj, depending on where you're doing it, weights, whether the weights is between the input layer and the hidden layer, or hidden layer between the output layer, delta would vary as defined earlier, and weight updation would happen. So this is how the softmax activation function is used, and this is how the multi-class classification works. Let's see a typical image processing application. We'll have a demo of it. To keep things simple, say suppose I have the 5 images, okay, as a matrix in a form of a 5 cross 5. So this can be written as, say for example, let me write it. So this is 0, this is 1, 1, 0, 0, 0, 0, 1, 0, 0, and so on. 0, 1, 1, 1, 0, and this is 1, 1. So we can have this. So in the form of a matrix. Now everything, whatever it may be, remember the Borasser was telling whatever may be the type of data, bring in terms of the image, and finally back in terms of the vectors and the matrices. So here we have, say, we have to train this. We have this as the training set. We will train it to a neural network. And once we give, we want it to identify and classify it to 1. So now it's a multi-class problem. Multi-class means what? Either it has to recognize as 1 or 2 or 3 or 4 or 5. One can be said as a classification, or it can be said as digit recognition also. Okay, but let me put it as a classification problem. Now let's consider it as 5 classes, right? So we'll have 5 output nodes, 1, 2, 3, 4, and 5 output nodes. Why? Because there are 5 classes. And how many input nodes will be there in the input layer depending on the data. This is 5 cross 5. So 5 cross 5 is equal to 25. So 25 nodes will be there in the input layer. So this is 1, this is 2, and so on up to 25. And this is the 24th one. Okay, 24th one, and so on. And this is the hidden layer. And there is no specific rule for the number of nodes that would be used in the hidden layer. So it's a trial and error method, and you would fix the number of nodes in the hidden layers. Once you do this, now you have the complete setup, and this is how we will we'll see the practically how it implements this card. Okay, so let me go to the session, MATLAB session. Yeah, let me close all this. Okay. Yeah. So multi-class problem. Yeah. Okay. Now, yeah. So now see here. Now it's a matrix, right? So we are concatenating in the z direction. So this is a 5 cross 5 dot. It will become 5. That is, say for example, just a minute. Sir, kindly share the MATLAB. Okay, okay, sure. Jamboard. Yeah, just a minute. Okay. So can you see the screen? Guys, hello? Okay, you can just see the screen. Okay.
Yes.
Yeah. So now we had 5 images, right, earlier. So one image and second image, and you need not join. Okay, just you can view 3 and say 4 and say, I'm just doing it randomly. Okay, quickly 5. So we had here the numbers. And we had this, right? So 1, it was written like this, and here 2, yes. So 2 was written like this, and we had 3 and 4 and 5, correct? Then we converted into terms of a matrix, right? So we had matrix, we had written, I told you how we had written it. Similarly, we will have Control C, Control V, Control V, Control V. Yeah, now we have got it. Now this one is whatever we are trying to show here is x of colon 1, right? So this is x of colon and 1. This one, okay? This particular thing. So this will be matrix of 1. So how matrix of 1? It will be like this. That already earlier I had told you, right? 0, 0, 1, 0, 0, and last row it was 0, 1, 1, 1, 0. Remember? So this is the first one. Next, last row here is, I hope it's visible whatever I'm writing. Okay, let me make it full border. Okay.
Yes, sir.
Yeah. The last one is, this one is the x of colon and colon comma, okay, it's not semicolon, colon comma and 5. What will be this? This will be having 5 matrix in term of matrix. So we have written that. So remember what was the first step that we said in a multi-class problem? Make everything in terms of vectors and matrices. Even the class needs to be in terms of vectors and matrices. So we are doing the step 1 and step 2 in the initial process. So this is number 1, this is number 2, this is number 3, this is number 4, if you see properly, if you number 5. So input, and this is the correct output. Correct output is what? See this diagram, this is the correct output. 1, 1, 1, 1, 1. So it's a 5 cross 5 matrix, only once in the diagonal. So, so 5 cross 5 unit matrix. So 1, 1, 1, 1. So we have made everything. So first and second step is done as per this. First and second. Third one, initial is the weights with the neural network with adequate, so random values, right? So one set of weight between the input node and the hidden layer, another set of weights between the hidden layer and the output node, correct? So one set of weights between this is nothing but W1. So 50 cross 25. So here you can see that it is 25 here and 50. So we are using 50 hidden nodes. So 50. So 50 is that is there, and 5 cross 50, right? So it is 50 here, it is there, and 5 output nodes. So these are the weights between input layer and hidden layer. These are the weights between hidden layer and the output layer. So we have randomly initialized it, okay? And then we are passing this initialized weight to a function, and we are training the neural network. So weights, correct input and output. So it will train the neural network and it will give the output. So let us see how it is trained going to the multi-class. So, so step 1 is done, 2 is done, 3 is done. So step 4 we have to do, that is pass the input and correct output into the neural network, calculate the error, and this delta is equal to AI. So we will do step 4 now. See there, we are going to the multi-class, okay? So multi-class, so weights, correct input, output, alpha, learning rate, 0.9. Okay, so now we have reshaped it. Fine. So this is the input and the correct output. Okay, now just see here. So output is nothing but we have to pass it, right? Here, output is output of hidden layer is weighted sum of the inputs. Input is going into the sigmoid activation function, and output of the hidden layer is nothing but output of the sigmoid activation function. So weighted sum of the inputs and output of the sigmoid activation function. Fine. Next what do we do? It is weighted sum of the inputs and then given to the softmax function, because this is output layer. So weighted sum of the inputs and then output of the softmax function is the final output. So y is the final output. Next, as per this equation, d minus y or delta is equal to e. So d minus y, delta is equal to e. Okay, and then this is done. So we have calculated the error between the correct output and the output of the neural network. Delta is calculated as per the cross entropy function rule, and now we are propagating backward. So error is nothing but weighted sum of the deltas. So we have to do this step. Error is nothing but weighted sum of the deltas, and delta is nothing but differentiation of the activation function to e. So let's try to do that. Fine. So now error is d minus y, delta is equal to e. That is at the output layer. Now, and the intermediate layer, remember it's a sigmoid activation function, and sigmoid activation function differentiation is nothing but output of the sigmoid activation function into 1 minus sigmoid activation function output into the error. So we have calculated that error is nothing but weighted sum of the deltas, and delta is calculated. That is this steps. These steps we have done this. Next, continue this until we reach about till the input layer, because there is only one. So we have done it. So it's only one equation we have. So we have stopped it. And then what is the next step that we have? The next step that we have is the updation of the weights. So weight updation would happen. So weight updation would happen. So weight updation is happening. Weight updation between input layer and hidden layer, between hidden layer and output layer, and run this as long as this epoch is called. So 10,000 time epoch. Now we have a trained neural network. So we have to validate it. So for this, we'll give the input, and we'll see what is the output, right? So we'll not give the correct output. So we'll see weighted sum of the inputs, and then sigmoid activation function, weighted sum of the another input, softmax function, and final output. So let's run this. So the training data and the validation data are same. Please note that in this demo. Okay, so let me run it. Change folder. So I should get the output as this is 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. So I should get this output, and so on. So let me show the output now. Yeah, so we've got the output, multi-class. So first one is 1, rest all is 0. Second one is, because it's a 2, right? 1, because I'm getting this output. 2, 3, 4, 5. So we are getting exactly this output. 2, 3, 4, and 5. So we have recognized the images correctly using this simple technique, right? Softmax. But I had told you practically that the real world data and the training data. So this is training data. Real data also will be slightly different. Say suppose I have this. Say I have corrupted it just for the demonstration purpose. I have corrupted it. So this is looking 1 for you. Some may say no, it's a 4. Well, let's see what the neural network will do. This is 2. Someone say it is looking like 3. Okay, this is 3 itself. This is 5. This is also 5 or S. So different perceptions, right? Let's see. But we have trained the neural network with these things 1, 2, 3, 4, 5. And say we have this. Again, we'll convert this into the matrix. How do we convert this? 0, 0, 1, 1, 0, and so on. 0, 1, 1, 1, 0, like this, so on. Okay. So if I do this, let me give this for the validation. I'll train this and then I'll validate this and then check how is the performance. So what it will recognize. Okay. So let me go real multi-class. So let me run. So let me run this. So this is the for the training clean data is used, but now it is corrupted, and then see what we are giving. So now you can see that this is the one which is corrupted. See here once I told you, right? 0, 0, 1, 1, 0, 0, 1, 1. So corrupted inputs we are given. This is corrupted. So let's see how it identifies. So we are validating it. Same steps. Inputs reshaped, weighted some of the inputs, sigmoid activation function output, weighted some of the inputs. Input means our output of hidden layers, and softmax function. So we have run it, and let's see what outputs we are getting. So first one, now see here, actual data would look like this. Earlier it was all ideal, right? 1, 2, 3, everything was like this. Now see practical data. From here, from here, the practical data. So which is the highest probability? This one, 0.9164. Yeah, some person said that it is looking like 4. So the neural network also took it as 4, and it is saying that it is with highest probability 4. Okay, because rest everything is very close to 0. Next, it is 2 or 3. Let's see what happens. Oh, it has given highest probability with 2. So it has told, no, this is 2. Next, we will see. With highest probability, this one. So 3, it has performed very well. See, this was 4, this was 2, this was 3 itself, it has told. Next, see what it will happen. Let's see, highest probability is, there is a confusion now. It is looking like 2, it is also looking like 3. For system, it is also taking like 2, and this is also taking like 3. So for us, it may look, sir, why, sir? Because for that, it is only numbers. Okay, 1, 0, 0, 1. So it has confusion, and see there is no clear cut winner. Earlier and all it is clear cut. Okay, there was 4, 2, 3, but here there is a confusion here. Here also, now you can see it is classified with highest probability with 5. Yes, more or less looking like 5, and it is correct. So this is how the real world data. So the training data was different, and the validation data is different. Now you see that how the performance varied when it was earlier. In earlier cases, all my training data, validation data was everything same. But now when it comes to the practical real world things, my data are different, and you can see that how. Okay, yeah. So we'll see that how it varies. Fine. Jyoti Prakash sir. Jyoti Prakash sir, are you there? Hello.
Yes, please.
Sir, I have another 20-25 minutes. Actual time was 2:30 to 4:30. I may take 5 or 10 minutes. Is it okay with you and the participants?
For us, it is okay. There is no issue.
Yeah. So I have solved. Let me summarize what and all I have done. Single layer neural network, problems of single layer neural network, how it is overcome in multi-layer neural network, and how binary classification we have done, and then multi-class classification using a real world example, say using images, whatever we could be done. Now let's go to the deep neural network or deep learning. Okay. Still we have time. I'll try to finish it by 4:30, but we'll see what can be done. Okay. Yeah. So let's go there. Now deep learning, right? Now what exactly? Earlier, you remember you had neural network here. Now it's deep neural network, because we know that most of the practical problems are linearly inseparable problems, and a single layer neural network cannot do it. So does deep neural network. So two or more hidden layers. So depending on the cost function, the learning rule would vary, and it is for us. It is, we know that cross entropy function would perform better. But even then, the deep neural network did not take off. Why? Because increasing in the number of hidden layers would put enormous burden on the computational load, and there was no computational resources to do such calculations earlier. Now we have it, but during that time, I'm telling. So there were certain drawbacks. What is that? We had certain problems. One is computational load. Number of hidden layers increases, weight increases, lot of calculations, and too much time, right? Too much weeks, months together. Now we have that power resources, but earlier no. But how is it still overcome? Using the GPUs, the graphical processing units, the computational load is taken. Okay. Now, what about the vanishing gradient? What is vanishing gradient? Now, say suppose you have used so many hidden layers. Now, error has to propagate from error has to propagate from the output to the input, right? Now, by the time it reach the input layer, it would have become completely zero. Once the error is zero, I mean, we cannot get the weights. So that means what? We are not at all training the layers which are there between the input layers and the first few hidden layers. They were left untrained. So that is the problem of vanishing gradient. And how is this overcome in case of deep learning? Deep learning is trying to solve all this problem, okay, in deep learning. This is using GPUs, and this is using the ReLU activation function. I think in the morning session, the sir was discussing. It's a ReLU, so rectified linear unit, right? So sir had told. So this, by using this activation function, why not sigmoid and all other functions? Now see, sigmoid and all, if you see the diagram, it was between 0 and 1. So minimum is 0 and maximum is 1. I think I had shown you the sigmoid activation. Yeah, 0 and 1. If it is a signum activation function between -1 and +1. But whereas the ReLU activation function, if you closely observe, it is here. Yeah. So for certain less than 0, it is 0. For here, it is basically it's a ramp function. So phi of x is equal to x for x greater than 0. It is 0 for x less than 0. So it is 0, and here it is x. So whatever x value takes, if it is 4, it is 4. If it is 5, it is 5, and so on. So with this, they could make sure that error is still active, and we could calculate the error at the hidden layers which are very close to the input layer, and that is how we could train the deep neural network. So that's how, by using a simple thing like ReLU activation function, we could solve the problem of vanishing gradient. And what about the overfitting problem? And earlier I had told you that by overfitting means simple regularization. Life is simple. Keep the model simple. That's one way. Regularization, or do validation, or better thing is do cross validation. Don't try to overfit it. You have a training data, run it so many times, epoch is more, and you are getting best performance for the training data. But what about for the practical data? You just now saw for the practical data, it may not do well. So that is why there should be a clear line between the training data and the real world data, how much you should train. Okay. So the differentiation of the ReLU function is also quite simple, and that's how we could solve this thing. But the other interesting solution for the overfitting that the deep learning provided was the dropout. I hope you know this dropout. What is the dropout? Let me explain you graphically. That means what? We will not, at a time, we will not try to train all the nodes. all the nodes may not be, some nodes are always dropped. Maybe some nodes in the hidden layer, some nodes in the input layer, somehow it is dropped randomly. How is it chosen? Randomly. So typically 50% of the hidden layers and 25% of the input layers are always dropped randomly. Say for example, when the first set of training data is given, I'll have these nodes. So these are the input nodes, these are the hidden layers, output node. So at the next, it may be something like this. So that's how we could do it. So dropout was very simple and yet very effective in eliminating the problem faced by the deep neural network, and which is how the deep learning is flourishing. Okay, and the other one was the regularization, validation, cross validation that I told you, and this is a computational load. Okay, now let's see how we can implement this same image classification using the ReLU and dropout, and also individually we'll do it. So let's try to go for the MATLAB implementation. Okay, so with this, yeah, we'll try to do this multi-class classification using ReLU and dropout. So here we have the input nodes. So how many number of input nodes will be there? 25, because the image is 5 cross 5. So it is 25 nodes at the input. Okay, and then output, how many layers? It's a multi-class problem, and number of outputs nodes is equal to number of output layers. I mean number of output images. So here 5 images needs to be classified. So 5 nodes at the output layer, and here we have chosen the so these many number of the hidden layers. So hidden layer 1, hidden layer 2, hidden layer 3. So W1 represents the weight between input and first hidden layer. W2 represents the weight between the first hidden layer and the second hidden layer. W3 represents between second and third, and so on. And between hidden layer and the output represents the weights of W4. So we have this setup. Using this setup, we'll try to do it. So 4 weights, correct input, input, and the correct output. One is using the ReLU activation function. We will see that because we have told that the overfitting, because overfitting is one very common problem, because people will ask, okay, how will I know that I have a overfit or not? Is there any solution to it? What is the practical solution? So I'm concentrating on that. So one, by using the dropout method, that is how we can do it, avoid the overfitting. And the other one is practically we will see that how the vanishing gradient is eliminated using the ReLU activation function. So one is vanishing gradient. This problem is solved using ReLU activation function, and the other one is using the dropout. Which problem? The overfitting problem. Okay, so let's try to do that, and let me go to the MATLAB. Let me close this. Okay, so let me close this, and yeah. So okay, using the ReLU activation function, these are the inputs. If you see that 1, 2, 3, 4, 5 inputs, correct outputs. We are initializing the weights W1, W2, W3, W4, same steps, passing it to the function with randomly initialized weights, input and correct output, calling it 10,000 times. So epoch is 10,000 times. We have got a trained neural network, deep learning, using deep learning technique. And we have got the input, we are validating it. So when we are validating it, again, we are passing it through the weighted sum of the input. Now ReLU is the activation function. Please consider it now. It's a ReLU activation function. Again, here, let me show this diagram so then it will be easy for you. Weighted sum of the input, then ReLU activation function output. Weighted sum of the inputs, ReLU activation function. Weighted sum of the inputs, ReLU activation function. At the last output, right? Weighted sum of the inputs, softmax function. That's the only difference. So softmax function. So ReLU, then ReLU, weighted sum of the inputs, ReLU, weighted sum of the inputs, ReLU, and then weighted sum of the inputs and softmax. When I say inputs to this particular node, it's from previous stage. Output of this is nothing but input to that. Okay, so please don't get confused. Set is telling input, and here it is y1, y2. No, it's not like that. So this is what, and we have got it. So let's see how it performs. For deep ReLU. So we are trying to address the vanishing gradient problem. So here, why vanishing gradient? Because we'll have multiple hidden layers. So that is why purposefully we have introduced different hidden layers. Hidden layer 1, 2, 3. So we have got multiple hidden layers, or we'll be able to do it correctly. So let me run it. So let me show you this deep relu inside what we have. Okay, so randomly initialized input, correct output. So here also, if you see that the steps is remain the same: input, weighted sum of the input, output of first hidden layer, output of second hidden layer through ReLU activation function, output of third hidden layer through ReLU activation function, output of the final output using softmax activation function. The correct output is there. Calculate the error, and then the cross entropy function will tell you that delta is equal to E. Do that. Propagate the error backward using back propagation algorithm. Error is nothing but weighted sum of the deltas, and delta is nothing but here differentiation of the ReLU activation function. It's not differentiation of the sigmoid function. It's a it's the differentiation of the yeah, here it is 1 for x greater than 0, 0 for x greater. So it's a simple differentiation. So that is implemented using this code. So differentiation of the activation function into error. So errors is propagated backwards, calculated it, and then the weight updation is happening as per the stochastic gradient descent method, and weights are updated. When this is called 10,000 times, we get a trained neural network. So let me run it. Okay, so trained neural network. So I've got it, and yeah, so we have got it. So this is the output. Yeah, now let's see. So deep ReLU. So we have run this. Now you see the output: 1, 2. In spite of using multiple hidden layers, 3, 4, and 5. So it has done extremely well. So the deep learning has overcome the problem of vanishing gradient by using the ReLU activation function at the initial stages of neural network, and the output we have softmax itself. Fine. Now dropout. Dropout is what? For overfitting. We should avoid overfitting. So dropout. So let's try to do that. MATLAB. So it is dropout. Fine. Same steps. Inputs 1, 2, 3, 4, 5. Correct outputs. Initialize the weights. Call this function, train the neural network. So once you have got this, trained neural network is there. Using this, validate it. So weighted sum of the inputs. Here we need not use the ReLU, but you can use combination that also. So when we are concentrating on dropout, we have used the sigmoid activation functions at the input, and then at the output, softmax function is used. Okay. So sigmoid weighted sum of the input, sigmoid activation function. Weighted sum of the input, sigmoid. We can combine it. Of course, we can combine it. To show separately, we have done it. Okay. And weighted sum of the inputs and softmax function of the output. So it should perform. And what is there in deep dropout? Let me go there. So this weights, randomly initialized input, correct output. So weighted sum of the inputs, sigmoid activation function, and then the dropout. Remember, dropout is do not consider all the nodes, but drop some of them. So we are calling the dropout function, randomly making it 0, some of them, and other outputs are updated. Again, weighted sum of the inputs, sigmoid activation functions, drop some of them and make it 0. That's what we are doing, nothing else. Okay. And then the third hidden layer, weighted sum of the inputs, sigmoid activation function, drop some of them, don't train them. Okay. Finally, the output, softmax function. This is random. Okay. Dropout, if you see, it's random. Okay. Randomly it is chosen and not the same thing. So randomly it is chosen, and then we are calculating it. So we are trying to do that. Let me go there. Where? Yeah. Deep report. So I've done this. Let me run. So we've got the output. Yeah, deep dropout. Now remember, we had used sigmoid activation function and not the ReLU, and then see the output now. Very close to 1. Very close to 1 here. 1, 2. Very close to 1. 3 output. Very close to 1. 4 output. Very close to 1. 5 output. This is just for the demonstration purpose. 3 hidden layers also is very less, right? So we have done how we could address the problems of deep neural network. Okay. Fine. Last comes the convolutional neural network. I think Bora sir had spent sufficient time on convolutional neural network. So it's 4:30 think I'll stop at this point. Convolutional neural network. So here I would have shown again with few examples, simple with numbers. I do not go into much mathematics and what the actual output would look like. And then finally how the calculations are done and what is mean pooling, max pooling. And then using a practical thing I would have shown, again not for the entire database, otherwise it would take too much. It has got 80,000 70,000 images, but we are taking only 10,000, and in that 10,000, 8,000 is for testing, 2,000 is for validation, and we could run it for MNIST database, handwritten recognition, digit recognition. So let me run it. It will take some time, but till then we can take some questions. Just a minute, I'll run that and I'll get back. So chapter 6 and yeah, so we are trying to run this. Let me make the epoch as 2. Okay, so yeah, epoch as 2 is there, and then see what's the performance accuracy. So it will take some time, 1 minute, 3 minutes. We have reduced the epoch, not 10,000, 20,000. I'm not giving, just 2 epochs, but internally everything, it's a small database, so it should run. Okay, so that's it from my end. I hope it was clear and I was able to reach the wide variety of audiences from different background. Assuming that you don't know anything and with some few basics, I could reach up to you. Please let me know if you have any questions. I've tried my best to reach out to you people. And currently I have also, we had working on diagnosis of visible diseases using the deep neural network we had done. Our work is under review currently. So that's the first for biomedical thing that we had used. So I couldn't show that particular output. Rest all is all introduction to deep learning using MATLAB. You can think it. Okay, so it was just to give you an idea like how MATLAB can be used for deep learning purpose. Okay, yes, madam. I'll try to share. Yeah, please, madam. Yes, madam. Yes, Meenu, madam. Dr. Meenu, madam, I'll definitely share. How can we calibrate the system used for AI? Okay, sir, whatever I have told, deep learning is a subset of machine learning, and machine learning is a subset of artificial intelligence. When I talk about artificial intelligence, we are trying to mimic the entire system, but I have tried to work with only with the deep learning and a few things that have worked. But the real artificial intelligence trying to mimic the entire thing, what would be the complete setup, how do you calibrate it? No, I have not worked, so I cannot comment on it. Okay, while masking the input to identify a specific shape from whole image, which mask should be used? Okay, so depending on masking the input to identify a specific shape from whole image, which mask should be used? Okay, so it depends on what type of filters, right? So for example, when you're talking about the deep neural networks, we are not using a specific, like in image processing, you're trying to confuse with the image processing. Like we have various predefined filters for recognizing particular shapes. But here in deep learning, for example, when I talk about the convolutional neural networks, even the convolutional filters weights that we are trying to obtain is through training. So they are filters or kernels obtained by using the training. Okay, so we're getting the mask. So once you take a specific set of circular images and you want to mask it, train with it, and it will be able to recognize it. So later then, it depends on how you process it. Can we use, I hope I've answered it. So it's basically on training. It's not predefined filters. Can we use deep learning neural network in prediction of ECG heart rates to detect the cardiac arrhythmia? And I'm not into biomedical. I've just started with that. But definitely, yes, they are using the deep learning neural network also. I've just read it. I've not worked on it. But definitely it can be used even for EEG and ECG also. They're trying to understand the biomedical signals using the deep learning neural network. So how will you minimize the noise factor in deep neural network in biomedical devices? Okay, so biomedical devices. in some of the multimedia things, if they are missing, if the data are missing, we make it as 0. I think that the same thing would be applied, but I cannot comment on the biomedical purposes. I'm sorry, a few of the questions are with respect to biomedical. I'm extremely sorry, Dr. David, sir. I'm sorry for that. I have basically worked on video hashing, multimedia data, and for retrieval purposes. And now we have started with the visible skin diseases in the initial work level. So we have not gone into EEG, ECG, and biomedical devices. We have specific set of databases, used it, deep learning, tried to get the features out of it, and then try to see what's the accuracy that we are doing. We have just done that work as of now with the research. Okay, let me see what is the output that we are getting now here. I've only run 2 epochs, and you can see that the output would be the 92.7. So accuracy is 92.7%. Not bad, right? So if I just increase the epoch to 5, I hope the time will be there till then. So 5, if I do, I had earlier run, so let me tell you, it will be around 96%. But if I make epoch of 30, 40 and all, I would be able to reach an accuracy of 97 to 98%. Okay, so that's how I would get it. So can I have your email ID? We'll get in touch with some of my queries for my research project. Sure, sir, sure. Yeah, I had to show all these things. Yeah. So this is my email ID, official email ID, and personal email ID. This is my phone number. So it's the deep learning technology is like exploding in a big way. By the time we finish this FDP, another algorithm would have come, another better performing thing would have come. So that is the rate at which it is progressing. So I am also a learner. I can say that I am also a learner. I have just started exploring because it has gone beyond boundaries. Okay, the deep learning. Jyoti Prakash sir, I think no more questions.
Yes, so we can wind up for today.
I'm extremely sorry because I have extended 10 more minutes. I'm sorry, participants.
No, that is, I hope, not an issue because I think all have learned a lot today, and your session was very much informative, and you have given all the participants in a best possible way. So thank you for today's session, and we are very much fortunate to have you here, and we definitely look forward in the future also for having such sessions.
Thank you, sir. Thank you, sir. It will be my privilege and honor to associate with you, and it will be my thing. By doing this, I feel that I will learn because there's questions, so many things that it makes me feel that there's a lot more things to learn. So thank you all for giving me an opportunity to present. Please continue. Sorry for the
Yes, sir. No, not an issue. Thank you, sir. Thank you for the entire team and from Gauhati University. And thank you for everything.
Yeah. Thank you, sir. Thank you for the. Thank you, sir. Thank you so much.
Sandeep, I hope there is one more question.
Yeah. Yeah.
In the chat box.
Oh, sorry. 1 second. 1 second. Yeah. Okay. So let me stop. 1 second. Before that, 1 second. I'll just run. Oh, I think I didn't run it for it. Okay, fine. Not an issue. Yeah. Yeah. Let me stop presenting it. Yeah. I'll just 1 minute. Okay. Okay. What are the questions? Okay, they're saying thank you, and then okay, accuracy what is meant by green data. Hello, yeah, sir. For the accuracy that I was trying to run, I think the accuracy was 98%. When I give the epoch of 30, accuracy was very close to 98%. For that, whatever I have trying to run the simulations. And the green data, I didn't get you, sir. Green data. Oh, okay, fine.
Okay, sir. Then thank you.
Yeah.
Thank you for your session.
Yeah, sure.
And, today will be winding up
Yeah.
for the first day.